Okay, so yesterday we learned, I am recording now, guys. Yesterday we learned about reflections. We learned about reflections over the x. That's when we have a negation of the entire function. The negative is out in front of the entire function. And then we have a reflection over the y where we just negate the x. That's where the negative is inside a grouping symbol with the x. So it's either inside parentheses, or it's inside the absolute value bar, or it's inside a square root. That's when it's inside. So these were the two we talked about yesterday. A negative out in front reflects it over the x. A negative grouped inside with your x reflects it over the y. Today we're going to talk about vertical stretches and compressions. Now, if this is your second go round in Acaag, if you took it last year, your teacher may have called them shrinks. I will not count off if you use the word shrink. But I think the word compression is a much better visualization of what's really happening. When I think of shrinks, I think of like shrinky dinks. Did y'all do shrinky dinks when you were little? You colored on that clear stuff and you put it in the oven and it shrunk in every single direction, didn't it? And when I think shrink in every direction. Well, if we say shrink here, we're really only talking about shrinking vertically. When I think about compress, and when I did my hands the other day and we made the parabola, when you compress, when you push down on the parabola, when I push down on it, what happens to it? It widens. Did it get any smaller? No. And when I think shrink, I think get smaller. It's not getting smaller. It just became wider because it's being compressed vertically. And that widens out your function. So I use the word compression, but it's widely accepted to use the word shrink, even though I think it gives you the wrong visualization. I think it makes you think it gets smaller. That's not what's happening. It's not getting smaller. It's just getting... Okay. So, with the functions that we study, we're really thinking of compressing them. So, vertical stretches are when something's multiplied out in front. But that something out in front is going to be greater than 1. Whatever that constant is that's multiplied out in front is greater than 1. Now, I'm using absolute value bars here because the positive and negative just tells us whether it's been reflected or not whether it's stretched or not. So if it's a number that's less than -1, say -3, the negative part means it's a reflection, but the 3 tells us it's a vertical stretch. So if we think in terms of absolute value, if the absolute value of whatever number multiplied out in front is greater than 1, then it's a vertical stretch. But if the absolute value of whatever out in front that's being multiplied is between 0 and 1, then we have a compression.
So a decimal?
Okay, so yeah, like an example of a vertical stretch would be like y equals 2x squared. An example of a compression would be y equals 1/2 x squared. An example of a stretch would be y equals -5 times f of x. The negative tells us reflection, but the 5 tells us stretch. Or another example of a compression would be like 2/5 square root of x. This number is less than 1, isn't it? So these would be vertical compressions, and these would be vertical stretches. So let's see how it's going to happen in the real world, in our application. Graph of y equals -x squared. This is really review from yesterday. That takes that parent graph that we know looks like this and reflects everything over. So there's our parent graph. Woo! Okay, so that the 0, 0 stays, but the 1, 1 flips down to 1, -1. The 2, 4 flips down to 2, -4. And then the -1, 1 flips down. And then a -2, 4 flips down. And so this is what we did yesterday, right? We know that this is just a reflection over the x-axis. And do we even need the table?
No.
No, we don't need that table. Okay, so since all of these are dealing with x squared, I'm going to go ahead and I'd like you to do this too. Go ahead and draw in that parent graph. Okay, so that's what that parent graph looks like.
Let's drop one graph on every single one.
For the examples, yes. Just makes it easier to see what's going on. So our parent graph for these is that y equals x squared. That's the parabola. A quadratic function.
Redo these next year.
We will. We're right in the middle of that unit in my Acaag class. We're having so much fun with quadratics. Did I tell you we can study the effect of gravity on objects? Because it follows a quadratic path. Yeah.
Is the what's like the quadratic formula? Like
Quadratic
negative,
formula?
Negative b plus b.
Oh yes,
something-
yeah.
something.
On Friday of next week, we're going to derive that formula. They're not going to memorize it. They're going to have to know where it came from, how to develop it. It's pretty cool.
That's not
It's cool little proof.
I don't like this. I don't like that.
No, you will. You will. That's one of those aha moments. Oh. Okay. So, this one has a 2 out in front. So we know we're multiplying by a number that's bigger than 1, which causes a vertical stretch. And it causes a vertical stretch by a factor of 3. No, that's not a 3. Let me try again. Of 2.
Is
Let's talk about the word. What does the word factor mean? Do you guys even know? Okay. Let me show you something. Let's say we had 2 times x plus 1. Do you realize there are 2 factors because I'm multiplying this times that?
they're what?
That's 2 factors. And so let's say I added an x minus 3 right here. Now I have how many factors?
4.
1, 2, 3.
Because you don't count that.
So those are factors, yeah. So factor just means something that I'm multiplying by. I'm multiplying by a factor of 2. Alright, now, it's a vertical stretch, so it only affects this function vertically. Well, our x's are horizontal, aren't they? So this vertical stretch isn't going to affect the x, but it's going to take the y and double it. So this point 1, 1 moves to 1, 2. This point right here, 2, 4, will move to 2,
2,
8.
Oh.
Double it.
Oh my gosh.
So,
Okay? Will 0, 0 move at all?
No.
No, because if I double 0, it's still 0, right? So negative 1, 1 will move to negative 1, 2. Yes, Ian?
So if it's a stretch, you double the y's. If it's a string or a compression, you double the x's.
No. If it's vertical, it's going to deal with the y's.
Oh.
If it's horizontal, it'll mess with the x's. And so we'll do horizontal one day. We're going to stick with just vertical today. So let's see if I would have gotten these same points if I plugged it into the table, since it's here. So this is 2 times, and this is where everything goes in parentheses. So negative 3 squared is 9. 9 times 2 is 18. Won't even fit. Negative 2 squared is 4. 4 times 2 is 8. Is there a point on my blue graph at negative 2, 8?
Yes, there
Yeah.
is.
Negative 1 squared is 1. And 1 times 2 is 2. Is there a point at negative 1, 2? 0 squared is 0. Times 2 is 0. 0, 0. 1 squared is 1. Times 2 is 2. 2 squared is 4. Times 2 is 8. And then 18 again. But those don't fit on the graph. So see, these points are on my graph. So I know I did it right. So a vertical stretch is going to affect the y's. And whatever this number is what you multiply your y by. Does that make sense? Yes, sir.
Yeah, I'm about to say that.
Okay. Now this one is less than 1. So this is going to be a vertical
Squash.
compression. I like the word squash though. I actually even like squash. By a factor of, I like squashing too.
1.5.
Of 1/2. Okay, so this 1, when I multiply by a half, it's going to come down here to half, isn't it?
Yep.
This 4 is going to go down to 2. This 9 is going to go down to
4.5.
4.5. 1, 2, 3, 4.5. And then the same thing is going to happen on the other side of my graph. So do you see how it kind of pressed it out? Vertical compression.
Yes.
And when you're pushing down on my hands, it made it wider. Yeah, wider.
So it's factors, it's coefficient.
Yes, the coefficient is a factor. Factor is something I'm going to multiply by. So that's what it gets multiplied by. Okay, any questions? All right. Now, I think you guys have a negative out in front of yours, which is good. Somehow I erased mine. Now, this was yesterday. Now, we know that the parent graph for the absolute value opens up like this.
Yeah.
And we don't have to know that because I'm going to give it to you. Oh, that was terrible. Let me totally try that again. That's embarrassing. I think I'm going to go ahead and draw this in with a line here. This is the parent graph for the absolute value. It's got a positive 1 slope on one side and a negative 1 slope on the other. There we go. And so I'm going to go ahead and draw it in on all of them. Because this is the parent graph we're working with. And it's easier for me because I don't have to do the dots and get out my ruler like you guys do. Okay, so my parent graph, which you'll be given, you don't have to memorize the parent graphs, you'll be given this, is y equals absolute value of x. And it's that B looking thing that opens up.
Should that be the upside down?
Okay, yeah, the first one is review from yesterday. So that negative out in front is just going to take and flip it, isn't it? It's going to reflect it right over that x-axis, and this is going to be coming down just like this. And we can test it using the chart, but we know what's going to happen. I totally missed. Let's see if I can move that around. Eh. I'm just not getting it. There we go. That's it. Okay, so we knew from yesterday that this is just a reflection over the x-axis. Nice little review for us there. Okay, the next two give us our vertical stretch and vertical compression. The first one is multiplied by a positive 3. What is that, guys? Vertical stretch.
A stretch.
By a factor of 3.
Good. It's a vertical stretch by a factor of 3. Okay, so 0, 0. If I multiply 0 by 3, it's really not going anywhere. This is 1, 1. If I multiply that y by 3, it goes to 1, 3. This is 2, 2. If I multiply the y by 3, it goes to 2, 6. This goes to 3, 9. And the same thing happens on the other side. Does this look like it's been pulled vertically? Yeah, vertical stretch. Now, the slope of the original, of the parent graph, is positive 1 on the right, negative 1 on the left. And the slope of the transformation is positive 3 on the right and negative 3 on the left. Didn't we just multiply the slope by 3? Yeah, that's what that multiplying out here does to this absolute value graph. So, on this one, the last one, it's got a 1/3, so it is a vertical compression. Okay, now some of these are hard to do. Like if I multiply 1 by a third, it's a third. It's a little tricky. If I multiply 2 by a third, it's 2/3. Still a little tricky. But if I multiply 3 by a third, what is that? 1. Well, that's good. If I multiply this 3, I get 1. And that's good enough for me because these are straight lines. And I can line that up nicely now. Alright, the next page is full of some U-tries for you. Here are the parent graphs we're going to be working with. I'm going to go ahead and give you a copy of this. This is exactly what it looks like on your test. This will be at the top of your test too. So I told you, I said, you do not have to learn these graphs. I'm going to give you a picture of them. Here they are. And you'll even say, this says, use the following parent graphs for the Unit 3 test. Cut straight off the test.
Stop there. Yeah, it's really.
It's really you should stop.
Yeah.
You would say at least 5 grams. Yes, sir.
This is what it would look like. If you multiply it by 3, it's going to go into U.
It's pretty easy.
U, it would just be squashed. It would be like that.
Yeah, I went ahead and posted them, so take a look. See if the ones you had a chance to do. I know you probably didn't get a chance to do them all.
I didn't reflect.
You didn't reflect anything?
Yeah, I got like the compression.
I gotcha. Like number 2 had the reflection and the compression.
Yeah, how do
So
you know
we
that?
had to flip it over. So this 1, 1 went to 1, negative 1, and then half. So flip over, the 2, 4 goes down to 2, 4, negative 2, excuse me. The 4, 2 would flip down to 4, negative 2, and then go up by half.
So everything with a negative reflects and then
Reflects first.
and also compresses.
And then compresses.
Number 6, does this look like there's any compression?
Bam.
Yeah.
With the negative on the outside.
Yeah, and then on the inside it reflects with the.
Yep.
Yeah, I understood what I did
Number 6
wrong.
column
I still got
has no compression.
Number 6 does not look like it has much of a compression. You're right. You're right. And I think it's really just because of my big sloppy pen.
Oh.
This one is more narrow. If I sketched it with pencil on graph paper, you could definitely see the difference. But this is the finest point that I get on the Mobi, so it makes it harder for you to see. And this graph was really small. If we'd used a bigger graph, it'd be easier. So the ones on the vertical stretch and vertical compression part, did you get those right even if you just kind of ignored the reflection? So we do want to practice putting them together though. So the reflection would come first and then we would do the vertical compression. Yes, ma'am.
I had a really hard time wrapping them on these tiny dots.
I know.
They did not look like my notes.
Okay. That's why I let you do your homework on graph paper because you can make it nice and big and see a lot. But if I ran off big graphs, I already sent like this unit was like way over 3,000 pages I copied. Yeah. So that's why we get puny, pitiful graphs. If you do it on your own graph paper, it looks a lot prettier. Okay, so this is quite similar to the one we did yesterday. So this main graph, the one that you're given, I think that first point, is that -8, -3 down here? And what is this point right here? Is that -6, 5? It's hard to see from the angle I'm at. -6, 5. Okay. And then I do believe this is -3, 2. And then -2, 2 rounds out the original graph. Y equals f of x. Okay. So this first one here says, okay, let's do a vertical stretch by a factor of 2. What's that going to do to all my y's? Yeah, it's going to double them, isn't it? So I get -8, -6, and -6, 10, and -3, 4, and -2, 4. So I'm going to double all those y's. So I go out to -8, I go down to -6. It's about right there. And then I go -6, +6. There it is. And then -3, +4, and -2, +4. I'm just going to connect the dots. Do you see how I vertically stretched it? Just vertically. That's all. Oh, that was supposed to be 10, wasn't it? That's not a 6, that's a 10. Is that right there? Okay, thank you. Completely didn't put it in the right spot here. Okay, from here to here. Now it actually looks right. Thank you so much, Bailey. Couldn't read my own writing. That's not good. Okay, Now number 2 takes this function f of x, and it's a vertical compression by a half. So what do we do to all these y's? Divide them by 2. So negative 8, negative 1.5. Negative 6, negative 2.5. Negative 3, 1. Negative 2, 1. Negative 8, 1.5. Negative 6, 2.5. 3, 1, 2, 1. Okay, so this calls my vertical compression. Pressed it vertically. Okay. This one reflects it over the y. And doubled it. So if I double it and then if I reflected it over the y and then doubled it, doesn't it just give me the opposite of all those x values? Yeah. So
Isn't that 8, 6?
it's the y's don't change, so it's positive 8, negative 6, and then positive 3, 4, and then positive 2, 4. Okay, and this last one, guys, I'm actually just going to graph it back on this first one, because this is going to take this vertical compression and shift it right 3 and up 1. So each one of these points would go right 3 up 1, right 3 up 1. The bell's going to catch me, so let me go ahead and tell you. On your homework, describe. Does anybody see the word graph? No. Tell in words what that means. That's all you have to do on that. This one you graph. Please use a different color. These you graph. Draw the parent graph first, and then do the shift.
When it's stretched, the x changes?
No. Nothing we've done today multiplies the x by anything.